Good afternoon. So in this session, we will solve a PD by the method of Lagrange. So I hope you have watched previous video in which we learned the origin and formation of partial differential equation. And in this session, our goal is to solve a partial differential equation, PD. Okay. So it's session 2. So here we will learn to solve. So basically, the solution of PD by, we call it Lagrange method. Okay. And what is that? So basically, Lagrange or characteristic equation. Okay, some people say Lagrange, or some people say auxiliary. Okay, so Lagrange auxiliary equation. Lagrange auxiliary equation is basically this: dx over p equal to dy over q equal to dz over r. Okay, and then we have to solve this as a system of differential equations. Basically, it will become ODE. Okay. When you get this, it will become an ODE, and then we have to solve that ODE. We will get the solution. Okay. So that is, suppose we get a differential equation, PD of this type, say P of x, y, z, and then we have del c over del x and plus q of x, y, z, and then del c over del y equals to r of x, y, z. Okay. So it is linear in P, Q, and even Z. Okay. There is no Z, but here you will get most probably. So it is a quasi-linear. Okay. So remember, you get any type of equation, whether it is semi-linear or quasi-linear, you have to apply this Lagrange method. Only Charpy method will be applied when we have a non-linear PD. That will be discussed in later videos. Okay. So you may write it down in short form. That is, this is P over P plus Q over Q equals to R. Okay. So we'll take our first example in our consideration to proceed with the problem. So let me write it down. It will be, say, y square z over x, and then p plus x z over q equals to y square. This is my PD. Okay, so I just have to identify that this is my p. Okay, it's my p of x, y, z, and then this is my q. And this pointer right here on the RHS is my R. Okay. So by Lagrange auxiliary equation, so just apply Lagrange, and then you write dx over b equals dy over q equals dz over r. And now simply put all these values. So dx over, what is p? It's my y square z upon x. This is my p equals to dy over x. Z equals to dz over y square. So now, when you consider two pairs while solving, okay, you have to consider two pairs. So you consider either one of them, or you can consider this, or you can consider this and this. So these three pairs are possible, okay, to solve this PD. So whatever you can consider first two, or the last two, or first and last. But anyway, you have to solve only two. Okay, you have to solve only two, because the goal is to find out, first solve this one pair and get in terms of either you get in x and y, you get here in y and z, you get here in x and z ultimately. So our goal is to find out this phi of C1, C2 equals to 0. Okay, our goal is to find out this. So basically we have to solve only two equations. Okay, so for our convenience, I'll consider the first pair. So consider the pair dx over y square z upon x equals to dy over xz. Okay. Or else, just a moment, because here I don't think so. It will give me something. No, I'll get it for sure. So the easiest thing that we can do is cancel this z and now proceed with the next step. So now it will begin. Take this x there. Else, it will be basically, I'll take it here. So x dx will be equal to y square over x dy. So it will be x dx cross multiplying. So x will come here and this y square upon x will come with this one. So x dx will be equal to y square upon dy. Now take this x here because it should be completely variable separable form. You got your nice equation which you have been solving since your lower standard. So it will be simply x cubed over 3 equals to y cubed over 3 plus some c1. Okay, and you can even take this at c1 by 3. So simply you get x cubed minus y cubed equal to c1 by 3. I'm calling another constant, say k1. It's a constant. So I'm saying k1 is nothing but my c1 over 3. So I got one equation, and similarly I have to consider one more pair. So first pair I have already considered this one and this, and now let's consider. See, if I consider first and third one, see y square is getting cancelled. So it is better to consider first and third one. Okay, go for the equation which looks simple to solve. That is recommended. Otherwise, if you're a hardcore player, you can consider any pair and go with this. No, there is no rule, something. Okay, now consider this. So I'm considering first and last pair, and in this I easily get y square getting cancelled and a nice equation, and it will help me as well. So from here I'll just check this point here. So I'll be getting dx over z over I think it's not dy, it should be dz. So let me check. Dz, I must, yes, that's dz. Okay. And then it will be dz. Now it's variable separable, so I can take this x here. So that means I'm getting x dx equal to z and dz. And now just simply integrate, so you get x square over 2 equals z square over 2 plus, I'm writing c2 over 2. Okay, now just keep this constant here. So I'll be getting x square minus z square equal to c2 over 2. I'm calling k2. Okay, so I got two nice equations. One is this, and another one is this. Now, when you get these two constants equal to some function of x, y, z, just simply write down. So therefore, phi of c1, not c1 because our constant is k1. So phi of k1 comma k2 equal to 0, or you can say phi of k1 equal to k2, or you can also say phi of k2 equal to k1. So you can choose any way convenient to you. So your solution would be phi of k1. K1 was y cube minus x cube, comma, and then k2 is x square minus z square. So this is x square minus z square equal to 0. This is also a solution, or you can write down phi of x square minus z square equal to y cube minus x cube, or you can write down phi of y cube minus x cube equal to x square minus z square. So these all three of them are solution to this PD. Okay. So in the case you consider our first lecture, and then you have this phi as an arbitrary function. So if you try to remove this arbitrary function, and by that this method, okay, p, q, and minus 1, ux, uy, uz, vx, vy, vz, okay, equal to 0. If you solve this determinant, I'm sure you will get this PD. The solution of this PD will be this. Where is it? Yeah, this one. Okay. At the end, you will get this quasi-linear PD. Okay. At the end, you will get this quasi-linear PD. You can try. So let's consider another problem 2. So problem number 2 is tan xp plus q tan y equal to tan z. Now in this equation I won't consider writing more of the things. So simply we will say by Lagrange. So by Lagrange method, I'm getting dx over, this is my p, okay, capital. Simply tan x equal to dy over x cube, tan y equal to dz over, I have tan z. So all you can do is, or in fact you can convert this tan and write down cot. So it will be cot x dx equal to cot cot y dy equal to cot z dz. And now just consider first pair. So I'll simply consider two pairs here. That is cot x dx equal to cot y dy. This is my first pair. You can consider any of them. So I'll take second one. So cot y dy equal to cot z dz. So just simply now integrate because they are already separated. So if you integrate here, so integration of cot is log of sine. So log of sine x equal to this quantity right here will give me log of sine y. And if all of them are log, so even write down the constant as log c. Okay, it will help you. So now just take this log quantity here. So I'll be getting log of sine x minus log of sine y equals to log of c. Now this quantity will give me log of sine x upon sine y equal to log c. So if I take the exponentials, I'll be getting c equal to sine x upon sine y. Instead write down log c1 because I'll be using another constant in the next equation. So c1 I got this, and now similarly you integrate this quantity here. So you get here again log of sine y equals to log of sine z. Okay. Plus written log c2. Now take this here, so you get log of sine y minus log of sine z equal to log c2, and then I'll be getting log of sine z equal to log of c2. From here I'll be getting sine y over sine z equal to. So one can write down phi of sine x upon sine y comma sine z equal to 0, or you can write down either of them in the form like phi of c1 equal to c2, so you can write down phi of sine x upon sine y equal to y upon sine z. This is also solution, or you can write down in this way sine y over sine z equal to sine x upon sine y. Also a solution. Okay. I hope it is considered. So basically, you have to just play with what the algebra that you had been doing. So now here it was quite easy one. Now from here, things will have different story. So problem number 3. Okay. Now this will be solved using the same method, but we have to do some more componendo dividendo kind of algebra. So if you have not read componendo dividendo, please watch another sections. Yes, now we go. So problem number 3 is b plus 3q equals to phi z plus So it's tan of y minus 3x. Okay, so we got this equation again, a quasi-linear form. So solution would be by Lagrange method. Lagrange method, you simply get d equal to q dz over r. Okay, and please be very sure while you're writing this capital P, capital Q, capital R, because they are functions of x, y, z. So you can even write down x, y, z, so that there is no ambiguity among while selecting. Okay. This P represents del z over del x, so it's a small p. Okay. Now dx over small p, it is simply 1 here, so write down here 1 equal to dy upon 3 equal to dz over will be tan of y minus 3x plus 5z. Well, now solving this equation looks very easy because we will consider first two pairs. Okay, so consider dx upon 1 equal to dy over 3. So I do not like fractions, so I'll transform them into in this form. Now I'll simply integrate, so I'll be getting 3x minus 3x equal to y plus 7. So from here I'll be getting 3x minus y equal to 7. But wait a second. I'll not write 3x minus y equal to 7. Instead, I'll write, I'll multiply with minus sign. So I'll be getting y first. Y minus 3x equal to some minus of 7, but this is a constant. So I'll replace by some another constant. I'll say y minus 3x equal to y minus 3x equal to some k1. It's a constant only. It will be helpful. It will come later. Don't worry. And now consider any two pair. So first one or third one, or second and third. Okay. So in that case, we will consider this one. Of course, you can consider first and third also. No issues. But I'll consider this one. That's not because it's easy, but just because I want to explain something to you. That is my goal. So tan of y minus 3x. Now here comes the tragedy, because for the variable separable method, you should have all this here. While variable separable method, it should only be function of y and should be function of x only while integrating. Okay. So here that is not the thing, because first part has no problem. Its first term has no issues. Dy over 3 has no issues. But what about this dz over 5z? But what this y and x is doing? So that's why I had recommended that y minus 3x should be taken as k1. So this part now will become k1. So dy over 3 will be equal to dz upon tan of k1 plus 5z. Now this is a constant. Entire quantity is a constant, and simply this is a function of z. So that was our goal. So this is a type 2 problem of Lagrange, okay, where one part is required to be used in the another part. Okay, no matter you consider the first pair, third pair, second pair, third pair, you have to use this fact. So in the case you're not getting the thing, suppose you're not getting how to solve this one, y minus 3x. So you should revisit the first problem and see you have there 3x minus y. So you can simply multiply by a minus and then change it as per your convenience. So I'm just multiplying by a minus sign just to make it convenient to write down this as a constant, because I need as a function of z only. So now this is simply like, you can consider 1 upon 5z plus c. Okay, what is the integration of this part? It's simply log of 5z plus c, and then the coefficient of z is 1 upon 5. Okay. In the same manner, c is nothing but your constant, so here you have tan of k1. So the same idea will be followed. Same idea will be followed here as well. So we will simply integrate now. So you can write down from Let's name this some equation 1. Okay. So from 1 I'm getting these things. Now I'll integrate in fact. So this will be 1 upon 3y equal to log of 5z plus tan of k1 and then 1 upon 5 then plus some c2. Okay. Now you can't keep this k1 here. Okay, so you have to resubstitute what is your k1. So it will be 1 upon 3y minus 1 upon 5 times log of 5z plus tan of what is given? It's y minus 3x equal to c2. Or you can multiply by 15 here. So you get 5y minus 3 times log of 5z plus tan of y minus 3x equal to, this will be 15c2, and I'll name it another constant, say this is k2. Okay, so therefore phi of k1 and k2 equal to 0. So you can write down in the blended form, so it will be phi of what you got there, k1 is y minus 3x comma this entire quantity, so phi y minus 3 times log of 5z plus tan of y minus 3x equal to 0. That's the solution. Just a moment. It's not the solution, it's a solution. Because one can consider the first and third one and get another solution. So both, all of them will represent the same PD. So you don't have to worry. Okay, like I'm considering first, they are considering second. It depends on you. You can consider any of them. Okay, because the ultimate goal will be the same thing. Problem number 4. So you can pause the video here and solve on your own first. If you don't get it, you can resume and watch it. Okay? Pause it and see while I'm trying. I'll simply integrate it, so I'll get log x log y, and since all of them are log, so it's habit to write down log k1, it's constant, and then I'll be getting log x over y equal to log of k1. So this implies x by y equal to k1. Now consider second and third, or you can consider first and third. So whatever you can like. We go for first and third. Ultimately, we have to do the same thing. So dx over what's that? Xz. Xz will be equal to dz over xy. So no matter whether you consider first and third or you consider second and third, there will be a problem because if I cancel this x, okay, so for z there is no problem, but for y there is a problem. So we need to get rid of this y, and if you consider second and third, so this y and y will get cancelled, and then you will get a problem with this x. So ultimately this requires a substitution from the previous story. So from here I'll substitute y, so y will be equal to x upon k1. It will be x upon k1, and I use this thing here. So first let's multiply all of them together. So it will be y dx will be equal to z. There is no issue with this thing, but this requires a substitution. So I said it is x over k1. So x over k1 dx equal to Z and dz. Now all of their variable separable method is completely fine now. So you can simply integrate. So x, it will be x square over 2 times k1 equal to z square over 2 and plus write down c2 over 2. So let's not write down c2, let's write down k2. Okay. This entire formula is in k1 and k2. So now resubstitute, so you get x square over what is k1? K1, that's what we have found. What is k1? X over y. Oh, this looks very weird. Instead, let me do this. Because it will be ultimately multiplied to each and every part. So instead of k1, I'm planning to do something else. But instead, let's substitute. K1 is x over y. So this x over y equal to, this 2 is gone. Then z square and then plus k2. So you can simplify this problem down and say it is simply your will be or I should have done something else, but no problem. You can keep in this form also. So you can just take this y there. So it will be y x square upon x minus z square equal to a2. Just take this x down. So you get yx minus z square equal to. So therefore phi of k1 and k2 equal to 0. So this implies phi of k1. What is k1? X upon y. So phi of x upon y, comma yx minus z square equal to 0. This is the required solution. So I hope you must have got this. If you have not, keep watching the video and keep practicing. I'll take one more problem and then we will stop. And then in the next session we will solve Cauchy problem. Okay, so let us consider solving one more problem. So this time again, you can pause the video and try this one. If you succeeded, if you did not succeed finding the solution to the previous problem, then you can try this one. Okay, so by the same idea, Lagrange. P over dy by q equal to dz over r. Now let's keep all the values. So dx upon p is what? Y equals dy over this is x, and then it looks very messy. Let's see. So consider the first part. So consider dx upon y equal to dy over x. Let's take this down here. So x dx will be equal to y dy. So it's simply x square over 2 equal to y square over 2 and plus write down c1 over 2. If I integrate, I'll get in this all. And then this 2 will be gone. So simply it will be x square and take this y square here and equal to c1. That I was waiting for because here they want the same thing. Now let's consider. So you can consider any of these three pairs. So instead, let's consider the second one. Okay. So now consider the pair. Consider the pair. Second one, the dy over x. So dy over x equal to dz over what do I have is x y z square. So x y z square. Sorry, x y z square. X y z square, and then I think this is x square minus y square, so it will be replaced by a constant because it cannot participate here. It cannot participate. Now this x and x will get cancelled to get this function y. So dy over dy equals to 1 over z square c1 times dz. And now simply integrate it. So it will be y square over 2 equal to, and you can have minus 1 upon z c1 plus c2. Simply now substitute, so it will be y square over 2 plus 1 upon z, and c1 was y square minus x square equal to c2. So since phi of c1 comma c2 is 0, so this implies phi of what is c1? It's y square minus x square comma y square over 2 plus 1 upon z times y square minus x square. Okay, this will be equal to 0. That's the required solution. Okay. So in this session, we have solved solution of PD by Lagrange method, and now we will continue in the lecture 3, and in that session we will conclude Cauchy problem for integral surface and some more problems from this type. Okay, it will require a lot of component dividend things, so we will continue next time. Thanks for watching.